Hi, I'm Ned, and I make games. In this video, I'll show you how to create a cool foliage shader for Unity's universal render pipeline, using only the shader graph. It's great for low-poly trees, complex trees, fields of grass, flowers, and more. These types of things don't look quite right using the default lit shader, since it lacks important features like two-sided normals, translucency, and wind deformation, so we'll fix that. But first, I'd like to introduce you to Core, who have very kindly sponsored this video. Core is a free PC game creation platform where anyone can create, share, and play games. No coding is required to start making games on Core, and I was impressed by the thousands of free music, sound, and art assets, which you can just drag and drop into your game. If you do code, you can even use the beginner-friendly programming language, Lua, to create your own game logic. Core has built-in multiplayer so that you can publish your game instantly for others to play. You know, I had to check out the Foliage assets since I've been working on lots of it. Look at all the pre-made models. There's a lot of customizability, and I was able to get the hang of the editor pretty quickly, so I think your Unity skills will serve you well here. These games were able to leverage these tools to create beautiful gardens, forests, jungles, and more. Since Core is powered by the Unreal Engine, your game will have high-quality AAA graphics. You can even make money with your games on Core. Core shares 50% of the revenue with its creators through the Core Perks program. I've learned that many Core creators have been able to pay their bills, buy their dream cars, and even quit their day jobs with the help of the Perks program. All in all, I was impressed during my time with Core, and I hope that you jump in and give it a try. Use the link in the video description to download Core for free and start creating your own game now. Thank you, Core, for taking a chance on small YouTube creators and sponsoring this video. Real quick, I want to thank David Crew and all my patrons, and my great community for your support helping make this video possible. Thank you all so much. If you'd prefer to read this tutorial, I've also made a written version, as well as a version about a text-only shader. You can find links to both in the video description. This tutorial was tested in Unity 2020.3 and Unity 2021.1 using the Universal Rendering Pipeline. If you're using a future version of Unity, check the video description for any important updates. This tutorial covers creating a foliage shader with the URP shader graph. It is complete with diffuse, specular, and translucency lighting. It supports all light types, their shadows, global illumination, and fog. We'll also look at wind deformation and two-sided rendering with normal mapping for use with grass billboards. This tutorial will not cover how to build any foliage models or textures. It will not show how to place grass blades or any other type of foliage around the game world, or support character interactions through physics or otherwise. I have tutorials planned for all of these topics in the near future though. I'll also assume that you know the basics of Unity, the Universal Render Pipeline, and the shader graph. You'll need to understand simple HLSL, which is the shader programming language, and what control keywords are, since we'll use both in custom functions. And although I'll give you a general overview of lighting techniques, normal mapping, and tangent space, I'll leave other tutorials to dive deep into them. Check out the video description for further reading. Get started by setting up your Unity project. You'll want to go through my custom lighting in the shader graph video, which provides the base for our shader. It covers adding lights, shadows, and global illumination support, as well as diffuse and specular lighting. Once you're finished with it, either duplicate or rename the completed shader files to foliagelighting.hlsl, foliagelighting.subgraph, and testfoliage.shadergraph. In foliagelighting.hlsl, rename mentions of custom to foliage. Then, in the foliage lighting subgraph, rename the custom function node's name field to match. Alright, let's set up a simple test scene to test the shader out on various types of common foliage meshes. Create a flat plane for the ground to test shadows. Then, create a sphere game object to simulate a simple low-poly tree. For a grass or bush billboard, create a quad game object and position it attached to the ground. Now to test for complex trees with many leaf cards, or double-sided quads, craft something in Blender, or another 3D modeling program of your choice. Create 3 quads, and rotate them so there's one in each plane. Create edges to split each into quarters, and then merge vertices to weld the planes together. Import this funny cube-like shape back into Unity and add it to your scene. Create 3 materials using the Foliage shader, one for each model, and then assign it. To better prepare for grass and leaf cards, add alpha clipping support to the shader. In the Test Foliage graph, click Alpha Clip in the Graph Inspector. Add a Float Alpha Clip threshold property and route it into the alpha threshold field of the master stack. Then, route the alpha output of the albedo texture sample into the alpha field of the master stack. In GIMP or another photo editor of choice, create a simple texture with an alpha channel for the cutout texture. In Unity, set alpha is transparency to true in the texture importer. Set up all your materials, making sure to add the alpha channel texture to the grass material. To make sure everything's working, let's test out a few lights. Also, to test global illumination, set all the foliage objects to static, and make sure double-sided global illumination is enabled on the grass and tree materials. Then, bake a light map. That all looks good. You might notice the grass and tree meshes are invisible on one side. This is due to something called backface culling. For meshes like the sphere, it allows Unity to ignore triangles on the inside of the model, but for double-sided geometry, like the foliage cards, we need to make some adjustments. In Test Foliage, turn on the two-sided option in the Graph Inspector. Now both sides are visible, however, the lighting is still incorrect. The mesh's normals point outwards from the front face, causing both sides to receive the same amount of light. I modified the shader to display normals here, and we can see that it's pointing in the Z direction on both sides. To fix this, we need to flip the mesh's normal vector when drawing on the back face. To support normal mapping, we have to do this before we transform the tangent space normal to world space. Create a subgraph called Calculate Double-Sided Normal. This will take in a tangent space normal and output a world space normal. This is front face node returns true if rendering on the front face. Use a branch node to switch between 1 and -1 depending on the value. The transform node cannot be modified to use a different normal vector, so we must recreate it. Construct a tangent to world matrix using the modified normal and multiply it with a tangent space normal and normalize. Again, for more information on tangent space, normal mapping, and the math behind it, check out the links in the video description. In the main graph, route your normal map sample through this subgraph instead of the transform node. In the scene, lighting should look correct on both sides, but you might have to turn off shadows to tell. Unfortunately, this shadow problem is difficult to fix within the shader graph since we cannot modify the shadow caster pass. Try adjusting the shadow bias settings in the light or URP settings asset. If this issue turns out to be a deal breaker for you, there is a solution in the text shader version of this video. One of the tricky things about foliage is that it should be translucent. Light filters through leaves, changing the way lighting and shadows affect them. Short of ray tracing, we can't have real translucency, but we can add several techniques to approximate it. The first is a method using what I call shape normals. Shape normals are separate normal vectors used exclusively for diffuse lighting. As opposed to regular mesh normals that we know and love, which describe a face's orientation on the mesh. Shape normals follow the overall shape of a plant. For instance, grass's shape normals should follow the terrain, while a tree's should point outwards from a central location, following the shape of a sphere or a cone. Using shape normals for diffuse lighting hides the fact that a lot of foliage is made up of a bunch of flat planes. You might be tempted to use shape normals for all lighting calculations. Regular normals, which I'll refer to as mesh normals from now on, are still useful for specular lighting and another technique that we'll get to later. The best thing to do is keep track of both. I'll cover strategies to do this soon, but first let's prepare the lighting algorithm. Open foliagelighting.hlsl. In the data structure, rename the current normal world space to mesh normal world space. This will hold the regular mesh normals. Add a new float3 field, shape normal world space. Go through the file, renaming the normal world space to the correct variable. Use the mesh normal in the reflection and Fresnel calculations, shape normal in the diffuse formula, mesh normal in the specular dot product, shape and mesh normals in the diffuse and specular node previews, and shape normal to mix global illumination. In the shader graph wrapper function, calculate foliage lighting _float, split the normal argument into mesh normal and shape normal. Set them in the data structure, then pass shape normal to the output sh and sample gi macros. In the foliage lighting subgraph, update the custom function to match the new wrapper function. Add a new shape normal property to the graph and route it into the custom function. In test foliage, let's temporarily route the double-sided normal into the shape normal. Return to your scene. Things should be clear of errors, but everything will look the same. Now to calculate the shape normals for each of our example meshes. For the sphere, which models a low poly tree or like a hedge, the shape normal is equal to the mesh normal, which is how things are at the moment. For the grass billboard, we want the shape normal to point upwards from the terrain. So we need to find a vector which points upwards along the grass card. This corresponds to the mesh's bitangent vector. Here I've modified the shader to output bitangents as color, and we can see that it's green here, pointing straight up. To support both shape normal options in the same shader, we can use an enumeration keyword. These allow us to change code depending on an option in the material. In the blackboard, add a new enum keyword called shape normal. The option is under the new property menu. Set the definition to shader feature, the scope to local, and the expose setting to checked. Add an entry for mesh normal and bitangent. We'll now be able to select an active entry in the material inspector. If you drag this keyword property onto the graph, Unity will create a branch node for you. It passes through the value connected to the currently selected keyword entry. Route a normal vector node and a bitangent vector node into the correct fields, and then into the shape normal field of the lighting node. In the scene editor, select the bitangent option for your grass material. That looks better already. Moving on to the tree, we'd like to approximate a spherical shape. There's not really a corresponding mesh value for this, so the best and most flexible option is to pre-calculate shape normals in a C# script and store them in the mesh's vertex color data. Create a C# script called foliage_shader_support.cs. Inside, add a list of transformed called normal foci. This script finds the closest focus to each vertex and calculates a vector pointing from the focus to the vertex. This will be the shape normal. Store the array of vertex positions from the mesh data and create a vertex color array. Convert all positions to world space. This is safe to do since the tree mesh is static. Loop through each vertex, normalizing the vector pointing from the nearest focus to the vertex. Store it in the color array, and then store the color array in the mesh. Finally, call the run function in the awake method. Back in the scene editor, add this script to your mesh game object. Create another game object for the normal focus, and position it near the center of your tree. Then, set it in the script. To test things out, create a vertex color node in your test foliage graph and route it directly into the base color field. Press play and you should see colors on the tree mesh. Looking at it through the scene view, the colors should roughly correspond to the little XYZ compass in the corner. Back in test foliage, remove the vertex color node and route the lighting back into the base color. Using another keyword entry, add the option to use vertex colors as shape normals. Back in the scene editor, change the tree material to use vertex colors, and then press play and check it out. If things look a little strange, you can try adjusting the position of the normal focus, adding more foci, or even just more vertices to the mesh. Shape normals create smooth, more realistic lighting, but the meshes still look opaque. If you view a light through a foliage card, it should glow a little. We can simulate this translucency effect using a simple subsurface scattering lighting algorithm. In my Lighting Formula Explorer program, which you can check out from the video description, I created a diagram detailing the algorithm. The effect is strongest when the view direction and light direction are opposite, which we can calculate mathematically by taking the dot product of the view direction and the negative light direction. This works well, but can make materials look a little flat. In reality, when light exits a transparent material, it changes direction slightly towards the surface's normal vector. By adding this normal scaled by a scattering coefficient to the negative light direction, we can simulate this effect. Let's ignore scattering for now and add a simple translucency to the lighting algorithm. In FoliageLighting.HLSL, add a float3 subsurface color variable, a tint applied to any light filtering through the mesh, and a float thinness variable, the translucent effect strength. In the wrapper function, add arguments for these new fields, and then set them in the data structure. In Foliage Light Handling, set the translucency light radiance, which is just the regular radiance tinted by the subsurface color. Calculate the translucency dot product from the negative light direction and the view direction. Similarly to specular highlights, tighten the dot product with a smoothness power and multiply by thinness. Finally, multiply the albedo, translucency radiance, and translucency strength together to add it to the final color. In the foliage lighting subgraph, add a new subsurface color and a thinness custom function argument. And a graph property for each. In test foliage, add subsurface color and thinness property as well. In the scene editor, set your main light to point straight in the Z direction and then take a look at it through any of your meshes. You may or may not see a glow depending on how your shadows are set up. The problem is that the object's cast shadows will attenuate translucency lighting as well. The best solution is just to remove shadow attenuation from the translucency radiance formula. This can cause translucency to shine in some places that it shouldn't, but in my experience, it's not very noticeable. The final call is yours. Let's return to scattering and add that to our algorithm. In FoliageLighting.HLSL, add a new float field to the data structure and a corresponding argument in the wrapper function. Then in Foliage Light Handling, calculate the scattered light direction by adding the scaled mesh normal to the negative light direction. Normalize it and then use it in the dot product formula. Update your custom function and add properties in both graphs. Then, in the scene editor, check out your materials. I find that it really adds a lot of depth. So that takes care of most translucent effects, but it would be nice to approximate translucency from indirect lights too. Since we can't change Unity's light mapper, and again, we don't have access to ray tracing, the best way to do this is to add ambient subsurface lighting strength, which gives foliage a constant glow. In Foliage lighting.hlsl, add a new float field to the data structure and a corresponding argument in the wrapper function. In Foliage global illumination, add a subsurface term to the indirect diffuse formula, multiplying the albedo, subsurface color, thinness, and ambient strength together. Then update the Foliage lighting custom function and add a property for ambient subsurface strength to both graphs. Take a look in the scene editor. I found that a little bit goes a long way. So far, all of these various lighting properties are constant over the mesh. It would be better to be able to read them from a texture, similarly to a smoothness or an occlusion map. However, there are so many properties that putting each in individual textures would slow down the shader quite a bit. We can combine 4 of them into one data texture, storing each in a color channel. You can choose to vary any 4 properties and organize them in any channel order. However, for this tutorial, I'll use the following layout. Red contains smoothness, blue contains specular highlight strength, green contains translucency thinness, and alpha contains the ambient occlusion. The lighting algorithm is almost ready to handle this, except that there's no specular highlight strength. I feel that this is pretty useful and prevents highlights in foliage creases, so let's add it really quick. While we're in there, let's also add a multiplier to fade the ambient reflection rim effect, which might not be very prominent on foliage. In Foliage lighting.hlsl, in the data structure, add a specular strength field and an environment reflection strength field. Then add variables for both in the custom function wrapper. In Foliage global illumination, multiply the indirect specular result by the environmental reflection strength as well as the specular strength. Then in Foliage light handling, multiply the specular value by the specular strength. Update the foliage lighting subgraph with the new custom function arguments, and add the corresponding properties. Add properties to test foliage as well, and then see how it affects all your materials. With that, we're ready for the data map. In the test foliage graph, add a new data map texture 2D field and then sample it. I like to keep around all the individual properties to use as multipliers for each channel, but you can delete them for more minimal materials. Route and arrange everything, and then be sure to double check that everything is hooked up correctly. Head into your texture creation program of choice and construct a simple test data texture. Draw a different pattern into each channel, preferably with soft gradients, so you can test a variety of values. Back in Unity, turn off sRGB and alpha is transparency in the texture importer, and then place this new texture in your materials. Now it's really easy to see how each value affects the lighting, and we're all set to create intricate plant textures. With that, we're done with the lighting for the foliage shader. However, it's still too stiff to feel like real plant matter. Besides translucency, plants' tendency to move with the wind is another big challenge. We can animate meshes in the shader very efficiently by passing new vertex positions to the master stack. This effect is perfect for wind. Create a subgraph called wind deformation. This will take in a vertex position and output a new deformed vertex position. Add a vector3 wind direction property as well as a float strength property. Multiply the strength by the direction and then add it to the position. Outputting the result. We can vary the wind strength over time and space using a noise texture. Add a texture 2D noise texture property and sample it using a sample LOD node. Do note that this must be a sample LOD node, since we're going to use this in the vertex shader stage. Next, we need to calculate a UV. World position should influence it, so use a swizzle node to select the X and Z coordinates out of the vertex position, and then multiply it with a new noise scale property. Similarly, multiply time by a noise frequency property. The output of the texture sample ranges from 0 to 1, but that would weight the deformation on the one side of the model. Use a remap node to change it to range from -1 to 1, and then use a split node to grab the red channel. Multiply it with the wind strength. Plants won't sway in a straight line due to wind turbulence. To simulate that effect, add a float turbulence strength property and a cross wind direction property. This cross direction will be perpendicular to the main direction. Multiply the turbulence strength by the wind strength, so it's all proportional, and then by the noise G channel, and finally the cross wind direction. Add the offsets together, and then add in the position. In the test foliage graph, add a new wind deformation node. Create properties for wind direction, strength, turbulence, noise texture, noise scale, and noise frequency. Route all of these into the wind deformation node, as well as vertex position in world space. For the cross direction, we need something perpendicular to the wind direction, but it still needs to look natural, meaning it shouldn't point into the ground, for example. The cross product of wind direction and the shape normal will do the trick. Finally, route the deformed position through a world to object transform node and into the position field of the vertex stage master stack. Open your image processor of choice and create a noise texture. Make sure that it has independent noise in the red and green channels. You can use any shape that you want, but I like the look of simple cloud or Perlin noise. In Unity, make sure that the texture importer has sRGB turned off. You can also safely turn off mip maps as well as compression if the wind motion ever looks jittery to you. Set up all your materials. And now we have wind, but I can see several problems. First off, wind causes the grass to detach from the ground. We need a way to scale wind strength over the mesh so that it's weaker near the bottom of the grass quad. Luckily, the UV's y-coordinate follow exactly the pattern that we need. First, in the wind deformation subgraph, add a float dampening property and multiply it with the final offset before adding it to the vertex position. In the main test foliage graph, we need to route the UV y-coordinate into this new field, but only for grass. Otherwise, the dampening should always equal 1. Another keyword will do the trick here. Add an enum keyword called wind strength with all the same settings as before. Create 2 entries, constant and UVY. Drag it out onto the graph to create a choice node and connect a float node with a value of 1 into constant and a UV node with a split node to grab the y-coordinate into UVY. Route the output into the dampening field. In the scene editor, change wind strength enum on your grass material to UV.y. That looks much better. Okay, so let's take a look at the tree. Here I can see 2 problems. First, imagine if a leaf texture was assigned to this material. The wind kind of causes it to stretch and distort in unnatural ways. To fix this, we should use the same position for all vertices when sampling the wind noise. This way, they will all move uniformly. Second, parts of the mesh attached to the trunk shouldn't move as much. Imagine the center vertex is anchored in this way. We can fix both of these problems by storing custom wind noise positions and dampening values in the mesh vertex data. Meshes can store a bunch of independent UV coordinates, and the shader graph can access 4 of them. The last set, referred to as UV3 or TextCore3, is usually unused, so we can use our C# script to store this wind data inside of it. Open Foliage Shader Support.cs. I'll go over this code quickly since it's kind of tangential to the foliage shader. Feel free to just download the file from the video description. Our goal here is to set the wind noise positions to a constant position. The center of the mesh's bounds will work just fine. And also set the wind dampening values to a value proportional to the distance from the closest focus. Noise anchors are stored in the XYZ channel of the TextCore3 vector, while the dampening will be in the W channel. Set the array in the mesh's UV stream, and it's ready to be read by any shader. In the wind deformation subgraph, add a new vector3 noise position property. Use that instead of the vertex position when calculating the noise UV. In test foliage, add another enum keyword called wind anchor. Add 2 entries, position and TextCore3. Drag the keyword onto the graph and route a position node in world space and a UV node in UV3 channel mode into the fields. Connect that into the noise position field of the wind deformation node. To support pre-calculated wind dampening values, add a 3rd entry to the wind strength enumeration keyword called TextCore3. Use a split node to grab the W component from another UV node in UV3 channel mode into this new option. In the scene editor, verify that your tree model has the script attached and that the TextCore3 index is 3. Switch the tree material keyword modes to TextCore3 and then enter play mode so that the script runs once. That looks a lot better to me. Feel free to modify this C# script as you need. The data is highly dependent on each individual model. But for now, it's time to address the last problem. If you look closely on any model, but it's especially apparent on the sphere, you'll notice that wind deformations don't affect specular lighting. They should, since wind deformations change the apparent normal of the mesh. The normal vector doesn't automatically update to match the new vector positions, so that we have to recalculate them, as well as tangents. It's difficult to do perfectly, since a shader only knows the position of one vertex at a time, but we can try to estimate it. The strategy here is to run 3 points through a wind deformation algorithm: the original position, and the original position slightly offset in the tangent and bitangent directions. We'll track how the deformation algorithm affects them, and then construct new tangent and bitangents by comparing them to the original value, and thus a normal vector from their cross product. We'll implement this formula in a new subgraph called wind deformation with orientation. Inside, output a position, normal, and tangent vector, and add properties for wind direction, cross direction, strength, turbulence, noise texture, noise position, noise scale, and noise frequency, as well as dampening. Create a wind deformation node and route all of the properties into it. Then duplicate it twice, leaving everything attached. Route a world space position into the top wind deformation node. The middle node will take the position nudged a small distance in the tangent direction. The bottom node needs the position nudged along the bitangent direction, but due to some quirks with the way the shader graph bitangent node works, it's a lot safer to calculate the bitangent yourself. Route the normal and tangent through a cross product node and then normalize the result. Subtract the top node's output from both the other outputs and take their cross product. The order of all these nodes is important to get the correct normal. Connect up the deformed position and normal outputs. For the deformed tangent, normalize the first vector used in the cross product. It's guaranteed to be perpendicular to the normal. In test foliage, replace the wind deformation node with a wind deformation with orientation node. Route the normal and tangent vectors through a world-to-object transformation node in direction mode before connecting them to the master stack. Now in the scene editor, you won't really notice any changes. This is because in the last step, we separated vertex position from the noise UV, and this partially determines wind offsets. In the wind deformation with orientation subgraph, we need to add the tangent and bitangent offsets to these noise positions. So that looks a lot better on the sphere. But not so much on the tree and grass. The specular shine seems almost random, which is an artifact of the distance between the vertices skipping over and not reflecting changes in the wind noise. Adding more vertices would certainly help, but perhaps the right solution is just to turn off normal recalculation when using extremely low poly meshes. In the main graph, add a Boolean keyword called windDeformsNormals_on. The on suffix is important to make sure that this keyword is editable in the material. Drag the property onto the graph twice, connecting the deformed normal and tangents into the on fields. Route a normal and tangent node, both in object space, into the off fields, and then connect these to the master stack. In the scene editor, turn off normal deformations for the grass and tree materials. As I mentioned, it's difficult to get normal deformation perfect without employing some very costly techniques. If this is really important to your game, you can continue refining the algorithm to match your model's needs. Perhaps have the algorithm depend solely on position, or make the noise a function so that you can calculate exact normals. And I think that about wraps it up for foliage in the shader graph. You can endlessly tweak things to fit your specific model. And speaking of that, I'd love to see your trees, grassy plains, and video game gardens. Please feel free to send me any screenshots that you have. For inspiration, here are all the material settings that I used to create the scenes in this video. This tree has a custom support script to set wind data, which finds connected pieces of the mesh, making sure that each chunk has the same wind noise position. Some effects currently not possible in the shader graph, like screen space ambient occlusion, really improve the final look of foliage, I think. You can add support pretty easily when 2021.2 releases, or you can take a look at the text shader version of this tutorial, which already supports it. Thanks so much for watching. Foliage is really fun to create, I think, and I've only really scratched the surface of foliage rendering here. I have several more videos planned, including one specifically on covering terrain with fields of grass. Please subscribe so you don't miss it. And don't forget to check out Core from the link in the video description to get started making your own game for free. Thanks again, Core, for sponsoring this video. And again, I want to thank all my patrons for helping make this video possible, and give a big shout out to David Crew, my next-gen patron. Thank you again so much. I really do appreciate it. If you'd like to download the project files from this video, including any other tutorial I've created, consider joining my Patreon. But if not, that's no problem. Either way, you can really help me out with YouTube's algorithm by liking this video, and be sure to subscribe for more game development tutorials. Thanks so much for watching, and make games.